The example is, if A and B are square matrices of order n such that column spaces of A and B are equal, then A is non-singular if and only if B is non-singular. Before starting with the proof, let's recall this remark first. Let A be a square matrix of order n, then A is invertible if and only if column rank of A is equal to n. Which means, to show that A is invertible, we have to show that the column rank of this square matrix is equal to its order. Right? So I'm going to use this result in the proof. Now what is given to us? That column space of A is equal to column space of B. And we have to prove that B is invertible. So we have to show B is invertible if and only if A is invertible. Right? That is non-singular. So suppose, let's take first A to be a non-singular matrix. So suppose A is invertible. It is given to us that CA is equal to CB. So let's take this CB, that is equal to CA. Because A is invertible, I can write this as IN into A, where IN is an identity matrix of order n, which is equal to the column space of the matrix, which is multiplied with the non-singular matrix. Reason: A is invertible. Now because CB is equal to CIN, right? And whenever the column spaces of the matrices are equal, we say that from here, therefore, their dimensions are also equal. Fine. Okay. What is the dimension of column space of identity matrix of order n? That is equal to n, right? And dimension of CB is nothing but the column rank of B. That is equal to n. And B is a square matrix of order n. So we have shown that the column rank of B is equal to its order, right? So therefore B is invertible by this result. So this implies B is invertible. Similarly, the other way. Conversely, suppose it is given to us that B is invertible and we have to show that A is invertible. So we have to start with this CA now, because I need to show that A is invertible. So let's start with CA, which is given to us as CA is equal to CB. So for A to be invertible, let's start with CA, that is equal to CB, which is equal to, because B is invertible, so it is column space of I and B, where IN is your identity matrix of order n. This is further equal to column space of the matrix, which is multiplied with the non-singular matrix, right? IN. And when the column spaces of the matrices are equal, their dimensions are also equal. So therefore, the dimension of column space of A is equal to the dimension of column space of IN. And dimension of column space of the identity matrix of order n is equal to n. And dimension of column space of A is nothing but the column rank of A, which is equal to n. And because A is a square matrix of order n, and we have shown that the column rank of A is equal to its order, right? So therefore, by the result, A is invertible. Thank you.